James Hopwood JeansThe Mathematical Theory of Electricity and Magnetism. All books on my channel are in public domain. Subsequent sections of the books are organized in playlists. Links provided in the last minute of the recording. Please subscribe, like and comment. Please be mindful that this book was printed in 1907. Conceptions and units might be incompatible with the modern ones. Chapter 2. Part 3. The Potential. 33. In moving the small test charge epsilon about in the field, we may either have to do work against electric forces, or we may find that these forces will do work for us. A small charged particle which has been placed at a point O in the electric field may be regarded as a store of energy. This energy being equal to the work, positive or negative, which has been done in taking the charge to O in opposition to the repulsions and attractions of the field. The energy can be reclaimed by allowing the particle to retrace its path. Assume the charge on the moving particle to be so small that the distribution of electricity on the conductors in the field is not affected by it. Then the work done in bringing the charge epsilon to a point O is proportional to epsilon, and may be taken to be V epsilon. The amount of work done will of course depend on the position from which the charged particle started. It is convenient, in measuring V epsilon, to suppose that the particle started at a point outside the field altogether, i.e. from a point so far removed from all the charges of the field that their effect at this point is inappreciable. For brevity, we may say the point at infinity. We now define V to be the potential at the point O. Thus, the potential at any point in the field is the work per unit charge which has to be done on a charged particle to bring it to that point. The charge on the particle being supposed so small that the distribution of electricity on the conductors in the field is not affected by its presence. In moving the small charge epsilon from x, y, z to x plus dx, y plus dy, z plus dz, we shall have to perform an amount of work. Minus, brackets x dx plus y dy plus z dz brackets, epsilon. So that in bringing the charge epsilon into position at x, y, z from outside the field altogether, we do an amount of work. Minus epsilon, line integral x dx plus y dy plus z dz, where the integral is taken along the path followed by epsilon. Denoting the work done on the charge epsilon in bringing it to any point x, y, z in the electric field by V epsilon, we clearly have V equals minus line integral between infinity and x, y and z, brackets x dx plus y dy plus z dz, giving a mathematical expression for the potential at the point x, y, z. The same result can be put in a different form. If ds is any element of the path, and if the intensity R at the extremity of this element makes an angle theta with ds, then the component of the force acting on epsilon when moving along, ds, resolved in the direction of motion of epsilon, is R, epsilon cosine theta. The work done in moving epsilon along the element ds is accordingly minus R epsilon cosine theta, ds. So that the whole work in bringing epsilon from infinity to x, y, z is minus epsilon line integral between infinity and x, y and z, R cosine theta, ds. And since this is equal, by definition, to V epsilon, we must have V equals minus line integral between infinity and x, y, z, R cosine theta ds. We see at once that the two expressions 6 and 7 just obtained for V are identical, on noticing that theta is the angle between two lines of which the direction cosines are respectively x over r, y over r and z over r and dx over ds, dy over ds and dz over ds. We therefore now have cosine theta equals large x over r, dx over ds plus large y over r, dy over ds plus large z over r, dz over ds, so that r cosine theta ds equals x dx plus y dy plus z dz. And the identity of the two expressions becomes obvious. If the theorem of the conservation of energy is true in the electrostatic field, the work done in bringing a small charge epsilon from infinity to any point P must be the same whatever path to P we choose. For if the amounts of work were different on two different paths, let these amounts be V of P of epsilon and V prime of P of epsilon, and let the former be the greater. Then by taking the charge from P to infinity by the former path and bringing it back by the latter, we should gain an amount of work brackets V of P minus V of P prime all times epsilon, which would be contrary to the conservation of energy. Thus V of P and V of P prime must be equal, and the potential at P is the same, no matter by what path we reach P. The potential at P will accordingly depend only on the coordinates x, y, z of P. As soon as we introduce the special law of the inverse square, we shall find that the potential must be a single-valued function of x, y, z, as a consequence of this law in paragraph 39. And hence shall be able to prove that the theorem of conservation of energy is true in an electrostatic field. For the moment, however, we assume this. 34. Let us denote by W the work done in moving a charge epsilon from P to Q. In bringing the charge from infinity to P, we do an amount of work which by definition is equal to V of P, epsilon, where V of P denotes the value of V at the point P. Hence in taking it from infinity to Q, we do a total amount of work V of P, epsilon plus W. This, however, is also equal by definition to V of Q, epsilon. Hence we have V of P, epsilon plus W equals V of Q, epsilon. Or W equals, brackets V of Q minus V of P brackets, epsilon. 35. Definition. A surface in the electric field such that at every point on it the potential has the same value, is called an equipotential surface. In discussing the phenomena of the electrostatic field, it is convenient to think of the whole field as mapped out by systems of equipotential surfaces and lines of force. Just as in geography we think of the Earth's surface as divided up by parallels of latitude and of longitude. A more exact parallel is obtained if we think of Earth's surface as mapped out by contour lines of equal height above sea level, and by lines of greater slope. These reproduce all the properties of equipotentials and lines of force, for in point of fact they are actual equipotentials and lines of force for the gravitational field of force. Theorem. Equipotential surfaces cut lines of force at right angles. Let P be any point in the electric field, and let Q be an adjacent point on the same equipotential as P. Then, by definition, V of P equals V of Q, so that by equation 8 W equals 0. W being the amount of work done in moving a charge epsilon from P to Q. If R is the intensity at Q, and theta the angle which its direction makes with QP, the amount of this work must be minus R epsilon cosine of theta times PQ, so that R epsilon cosine of theta equals 0. Hence cosine theta equals 0, so that the line of force cuts the equipotential at right angles. As in a former theorem, an exception has to be made in favor of the case in which R equals 0. 36. Instead of P, Q being on the same equipotential, let them now be on a line parallel to the axis of x, their coordinates being x, y, z and x plus dx, y, z respectively. In moving the charge epsilon from P to Q the work done is minus x, epsilon dx, and by equation 8 it is also brackets V of Q minus V of P end of brackets, epsilon. Hence, minus x dx equals V of Q minus V of P. Since Q and P are adjacent, we have, from the definition of a differential coefficient, partial V with respect to x, equals V of Q minus V of P over dx, equals minus x. Hence we have the relations x equals minus partial of V with respect of x, y equals minus partial of V with respect of y, and z equals minus partial of V with respect of z. Results which are of course obvious on differentiating equation 6 with respect to x, y, and z respectively. Similarly, if we imagine P, Q to be 2 points on the same line of force we obtain R equals minus partial of V with respect of S, where partial of, in respect of S, denotes differentiation along a line of force. Since R is necessarily positive, it follows that partial of V over ds is negative, that is V decreases as S increases, or the intensity is in the direction of V decreasing. Thus the lines of force run from higher to lower values of V, and, as we have already seen, cut all equipotentials at right angles. 37. At a point which is occupied by conducting material, the electric charges, as has already been said, must be in equilibrium under the action of the forces from all the other charges in the field. The resultant force from all these charges on any element of charge epsilon is however R epsilon, so that we must have R equals 0. Hence x equals y equals z equals 0, so that partial of V with respect of x equals partial of V with respect of y, equals partial of V with respect to z, equals 0. In other words, V must be constant throughout a conductor for electrostatic equilibrium to be possible. And in particular the surface of a conductor must be an equipotential surface, or part of one. The equipotential of which the surface of a conductor is part has the peculiarity of being three-dimensional instead of two-dimensional. For it occupies the whole interior as well as the surface of the conductor. In the same way, in considering the analogous arrangement of contour lines and lines of greatest slope on a map of the Earth's surface, we find that the edge of a lake or sea must be a contour line. But that in strictness this particular contour must be regarded as two-dimensional rather than one-dimensional, since it coincides with the whole surface of the lake or sea. If V is not constant in any conductor, the intensity is in the direction of V decreasing. Hence positive electricity tends to flow in the direction of V decreasing, and negative electricity in the direction of V increasing. If two conductors in which the potential has different values are joined by a third conductor, the intensity in the third conductor will be in direction from the conductor at higher potential to that at lower potential. Electricity will flow through this conductor, and will continue to flow until the redistribution of potential caused by the transfer of this electricity is such that the potential is the same at all points of the conductors, which may now be regarded as forming one single conductor. Thus, although the potential has been defined only with reference to single points, it is possible to speak of the potential of a whole conductor. In fact, the mathematical expression of the condition that equilibrium shall be possible for a given system of charges is simply that the potential shall be constant throughout each conductor. And when electric contact is established between two conductors, either by joining them by a wire or by other means, the new condition for equilibrium, which is made necessary by the new physical condition introduced, is simply that the potentials of the two conductors shall be equal. The Earth is a conductor, and is therefore at the same potential throughout. In all practical applications of electrostatics, it will be legitimate to regard the potential of the Earth as zero, a distant point on the Earth's surface replacing the imaginary point at infinity, with reference to which potentials have so far been measured. Thus any conductor can be reduced to potential zero by joining it by a metallic wire to the Earth.